Hello everyone and welcome back. In this video we're going to talk about finding confidence intervals for means just like we did for proportions. Now recall that the central limit theorem states that the sampling distribution model for the mean will be normal with mean that is equal to the population mean mu and standard deviation given by the population standard deviation sigma over the square root of n. And this will be true if the population distribution is normal, regardless of the sample size, or the sample size needs to be at least 30 for populations that are not normally distributed. Now, until now, we had been working with the normal model under the assumption that the population standard deviation is known. However, the population standard deviation is generally unknown, and we approximate it by using the sample standard deviation S that we collect from our data. However, this causes variability in our results. And to fix this variability, we will introduce another type of sampling distribution models called the student's T distribution. Now, the T distribution was developed by William Gossett, who published his results under the pseudonym Student. He was the chief executive brewer for the Guinness Brewery in Dublin, Ireland, and policies had prevented him to publish his work under his name, which is why he chose the pseudonym Student. Now, Gossett worked on developing the best stout possible, which is a thick, dark beer, and his experiments often dealt with small sample sizes, often 3 or 4. When he calculated the mean of his samples, Gossett wanted to compare them to a target mean to judge the quality of his batch. And he followed common statistical practice at the time, which was to calculate z-scores and then compare them to a normal model. However, he noticed that with samples of this size, his tests weren't quite right. Too often, the batches that he had rejected and then sent back for further testing turned out to be okay. He later earned a graduate degree in statistics and chose to work on this problem, and he discovered the T distribution, which are similar to the normal distribution, but are more suitable for working with small sample sizes. And like with the chi-square distribution, the T distribution depends on a parameter called the degrees of freedom. And the figure on the right shows the T distributions for 2 and 5 degrees of freedom, given by the red and the green curve. Now, these are unimodal and symmetric, but are much flatter than the normal distribution and have thicker tails. Now, notice that as we increase the number of degrees of freedom, then the closer the T distribution will become to the normal distribution. And if we have infinite degrees of freedom, then the T distribution will be exactly normal. Now, to find the area under the T distribution, we will use table T, which will be structured similarly to the chi-square table. Now, the table only gives certain critical values and certain degrees of freedom. So let's take a look at some examples of using the T table. So let's find the critical value that corresponds to a probability of 0.05 to the right of T star with 5 degrees of freedom. So let's draw a diagram of the critical value that we're looking for. So to the right of T star is a area of 0.05. And we're working with 5 degrees of freedom. So we look for 5 degrees of freedom in the T table, and along the first row lists the right tail probabilities. So we want to find a right tail probability of 0.05, and with 5 degrees of freedom, this tells us that our critical value is 2.015. So T star is 2.015. Now let's find the critical value that corresponds to a confidence level of 95% with 15 degrees of freedom. So for 95% confidence, this tells us that the central area is 0.95. And so we want to find the critical value that corresponds to 95% confidence, which means that the area in the tail is going to be half of 5% or half of 0.05. So this will have a right tail probability of 0.025 and we're working with the t-distribution with 15 degrees of freedom. So looking in the t-table, we will locate 15 degrees of freedom and a right tail probability of 0.025. Alternatively, there is a column which lists the confidence levels. Since we were looking for a 95% confidence, the critical value t star is going to be 2.131. So now let's find the critical value, which corresponds to a probability of 0.9 to the left of t star with 19 degrees of freedom. So the area to the left is 0.9. Since the t-table gives right tail probabilities, we need to find the area to the right of t star. And using the complement rule, we have an area of 0.1 to the right of the critical value with 19 degrees of freedom. So now looking up 19 degrees of freedom and a right tail probability of 0.1, we find that the critical value is 1.328. So now let's look at a few examples for finding an interval estimate of the following probabilities. So let's suppose we want to find the area to the right of 1.693 with 19 degrees of freedom. So in our t-table, we're going to locate 19 degrees of freedom, and then we'll look across the row to see where 1.693 falls within the table. Notice that 1.693 is between 1.328 and 1.729. And at the top of the column gives us the right tail probabilities. So let's write down what the t-table is telling us for the right tail probabilities of these two values. So the area to the right of 1.328 is equal to 0.1, and the area to the right of 1.729 has an area of 0.05. So the area of the region to the right of 1.328 is 0.1, and the area to the right of 1.729 has an area of 0.05. And so we want the area to the right of 1.693 Now, since the area to the right of 1.328 is 0.1, and the area to the right of 1.729 is 0.05, that tells us that the area to the right of 1.693 is between 0.05 and 0.1. And so mathematically, we can write this using an interval. So the area to the right of 1.693 is between 0.05 and 0.1. So now let's find the interval estimate for the area to the left of negative 2.009 with 30 degrees of freedom. So we want the area to the left of negative 2.009. Now keep in mind that the t-table gives us the area to the right of the critical values. So we're going to use the property that the t-distribution is symmetric and so the area to the left of negative 2.09 is the same as the area to the right of positive 2.009. So mathematically, we can write this as the area to the left of negative 2.009 is equal to the area to the right of positive 2.009. So now looking up 30 degrees of freedom in our table, we're going to locate where 2.009 falls within the values. And notice that it falls between 1.697 and 2.042. So now let's write down the right-tail probabilities that the table is giving us for those values. The table tells us that the area to the right of 1.697 is equal to 0.05. And the area to the right of 2.042 is equal to 0.025. Okay, so the area to the right of 2.042 is 0.025, and the area to the right of 1.697 is 0.05. And so that tells us that the area to the right of 2.009 will be between 0.025 and 0.05. And because of symmetry, that tells us that the area to the left of negative 2.009 will be between 0.025 and 0.05. So now let's find the interval estimate for the area to the right of 4.025 with 45 degrees of freedom. So we'll locate 45 degrees of freedom in our t-table, but notice that 45 degrees is not listed in the table. So the rule is to round down to the closest degrees of freedom, which is going to be 40. Then we're going to locate where 4.025 falls within the table. And if you look across the row with 40 degrees of freedom, we notice that 4.025 falls to the right of the table. So the closest value is 3.307. So let's write down the probability that the table is giving us. So the table tells us that the area to the right of 3.307 is 0.001. So the area to the right of 3.07 is 0.001. And we want to find the area to the right of 4.025. Now, since the area to the right of 3.307 is equal to 0.001, that tells us the area to the right of 4.025 will be less than 0.001. And as an interval, this area will be between 0 and 0.001. The sampling distribution model that we will use when the population standard deviation is unknown is the t-distribution with n-1 degrees of freedom, where n is the sample size. So now let's take a look at the assumptions and conditions required to use this model. So we have the usual independence assumption, which can be checked by randomization. Now the 10% condition is typically not a concern for means, and so we won't check for this. Now the other assumption is the normal population assumption, which says that the population should be normally distributed, or the sample size needs to be at least 30 if the population is not normal. And so we can check for this by using the nearly normal condition, which says that the sample data should be unimodal and reasonably symmetric. Now, if those assumptions and conditions are met, then we can find a confidence interval for the mean, which is called a one-sample t-interval. Now, the sample estimate is y bar. This is the sample mean. The critical value is going to be a t-value, which will depend on the level of confidence and the number of degrees of freedom. And the standard error is given by the sample standard deviation s over the square root of n. So let's take a look at a few examples of finding the confidence interval. So the housing market has recovered slowly from the economic crisis of 2008. Recently, in one large community, realtors randomly sampled 36 bids from potential buyers to estimate the average loss in home value. The sample showed the average loss from the peak in 2008 was 9,560 with a standard deviation of 1,500. So what are the assumptions and conditions that must be checked before finding a confidence interval, and how would we check them? So we have the independence assumption, which says that the loss in value of one home should not affect the loss in home value of other homes. So to check for independence, we look for randomization. So we're given that realtors randomly sampled 36 bits, so we have a random sample. And so this condition is met. Then we have the normal population assumption, which says that the population distribution should be normal. Which will be checked by the nearly normal condition. So either the sample data is normal or nearly normal, so unimodal and reasonably symmetric, or the sample size is at least 30. And so we have a random sample, so the randomization condition is checked. And to check for the nearly normal condition, we can either look at the histogram to see if it is nearly normal, or since the sample size is at least 30, then we can assume that this condition is met. So now let's find the confidence interval So the confidence interval is given by y bar plus or minus the critical value times the standard error. So we're given that the average mean loss is 9560. The standard deviation is 1500. And we have a sample of 36. So now to find the critical value, we need to determine the degrees of freedom. And the degrees of freedom is given by n minus 1. So that's 36 minus 1, which is 35. So now we'll look in the t-table to find the critical value. So we want to locate 35 degrees of freedom. Notice that 35 degrees is not listed in the table. So we're going to round down to the closest, which is 30 degrees. So the critical value for 30 degrees of freedom and 95% confidence is 2.042. Now the last thing that we need is the standard error, which is the sample standard deviation over the square root of the sample size. So that's 1500 over the square root of 36, which is 250. So now we can find our confidence interval. So we have 9560 plus or minus the critical value, which is 2.042, times the standard error, which is 250. So that's 9560 plus or minus a margin of error of 510.5. So our confidence interval is from 9,049.5 to 10,070.5. So we could say that we are 95% confident that the true mean loss in home value is between 9,049.5 and 10,070.5. So let's take a look at another example. Suppose a researcher selected a random sample of 50 adult males and recorded their daily intake of dairy products. It was found that their average daily intake was 756 grams with a standard deviation of 35 grams. So let's find a 95% confidence interval for the mean daily intake of dairy products for men. So let's first check the assumptions and conditions. So we have independence. So the daily intake of dairy products in a man should not affect the daily intake of dairy products in other men. So we're going to check for randomization. So here we're given a random sample of 50 adult males. So this condition is met. We have the normal population assumption. So the population should be normal so we're going to check the nearly normal condition. And so the sample distribution should be normal, or the sample size is at least 30. So we have a sample of 50 adult males, which is greater than 30. And so this condition is met. So now to find the confidence interval, we take the sample estimate plus or minus the critical value times the standard error. So we're given that the average intake is 756 grams and the standard deviation is 35 grams. Our sample size is 50. So to find the critical value, we need to find the degrees of freedom, which is n minus 1. That gives us 49 degrees of freedom. So notice that in our t-table, we don't have 49 degrees of freedom, so we're going to round down to the closest. So in this case, we're going to round down to 40 degrees of freedom. So the critical value for 95% confidence and 40 degrees of freedom is 2.021. So the last thing that we need is the standard error, which is the sample standard deviation over the square root of n. So we have 35 over the square root of 50, which is approximately 4.9497, and so on. And now we're ready to find the confidence interval. So we take our sample estimate, which is 756, plus or minus a critical value of 2.021 times the standard error of 4.9497. So we have 750 plus or minus a margin of error of 10.0034. And so our interval is from 746 to 766. So we can say that we are 95% confident that the true daily intake of dairy products in adult men is between 746 grams and 766 grams. Now, in the rare case that the population standard deviation is known, then instead of using the t-distribution as the sampling distribution model, we should use the normal distribution instead. And so to find the confidence interval, the critical value is now a z-score, since we're using the normal distribution, and then the standard deviation is calculated by taking the population standard deviation sigma over the square root of n. And that concludes our lesson for this video. In the next video, we will look at determining the sample size for means, and I'll see you then.